right, everybody, hello. Welcome to my at-home whiteboard. We're going to talk about work. All right, when we talk about work, we are talking about force. We have 10 newtons to each of these boxes. Force being applied over a distance. All right, so again, we're talking about forces, all right, but this time we're going to add another variable. We're going to talk about distance, okay? So think about how much work it takes to move something. You apply a force, all right? It's going to take more work to move an object 20 meters versus moving an object 10 meters. And the formula is basically just multiplying the force times the displacement. So here, work equals 10 newtons times 10 meters, all right? And that's going to give us 100 Newton meters, all right? But we're not going to keep that in Newton meters. The unit of work is joules. We're going to write that as capital J. So the unit, we'll put that here, unit of work is joules. All right, so let's compare the work required with an applied force of 10 newtons moving an object 10 meters. And we're going to compare that to the force applied of 10 newtons to move the object 20 meters. So work equals 10 newtons times 20 meters. All right, so that's going to give us 200 Newton meters. All right, so we just derived a new unit. All right, work equals 200 joules. All right, so we applied it across twice the distance. It's requiring twice the amount of work. All right, pretty simple. You're just multiplying the force times the distance. All right, so let's change my diagram a little bit here. Let's change this arrow. All right, let me erase all this. Let's apply our force at an angle. All right, so if we're applying our force at an angle, the actual component of force, right, that's going to matter is our horizontal component, because we're trying to move the object horizontally. So the component that's going to matter is the component that is moving, the component of force that is moving the object parallel. Okay, we really don't care about any force being applied down, pushing our object down in the perpendicular direction towards our motion. We only want what's moving parallel. So let's draw our parallel component. We're going to say it has an angle. It's making an angle with the motion, an angle with the direction of the motion of 30 degrees. All right, for both cases. All right, so right here we can kind of extend that out, say that that was a triangle. So that would be our cosine component. And so work is equal to force times the distance, in this case, times the cosine of theta. All right, so again, very simple. We're applying 10 newtons of force is being applied, but how much work, the question would be how much work is actually taking place. So work equals force of 10 newtons over a distance of 10 meters, but we only want the parallel component, so we need the cosine of 30 degrees. All right, and I solved this already. All right, so this would be work. You can solve this and check yourself. Would be 69 joules. All right, let's compare the work being applied at an angle across a distance of 20 meters. So work equals the force of 10 newtons. We're applying 10 newtons of force across a distance of 20 meters. But we only want the cosine component because that is the component that is parallel to the motion. All right. So we are looking at the angle that is being made with the motion. All right. And I did solve this. All right. All right, so again, we still have way more work being done, needed to occur when we apply the force over a greater distance. So again, it's actually pretty simple. We're just using the cosine, the adjacent angle that's being shown. All right, next concept we're going to look at. Just real simple. This will be a question in one of your homeworks. How much work is getting done if the angle, all right, this is 10 newtons. If the angle of the force being applied is a right angle, how much work is getting done? Well, the cosine, force times distance times the cosine of 0 degrees, the cosine of 90 degrees, I meant to write that, 90 degrees is equal to 0. And you can just picture this. If you're applying a force straight down, not at all in the direction of the motion, no work will get done. So the work will be equal to 0 joules. All right. All right, so what would this look like if we were to draw a graph of the force? Okay, force is our y-axis, and distance or displacement is our x-axis. All right, and we are going to assume, we've taken a look at a constant force being applied. All right, so constant force being applied, and we're just going to specify a displacement. We just said that force times displacement is going to give us work. So if we're taking a look at a graph, the area under the curve, all right, the area under the curve, you're multiplying force times displacement, right? Base times the height. So the area under the curve of a force times displacement curve is going to give us work, okay? That's assuming right here that the force is constant. The next video we're going to talk about changing force. It's going to look a little bit different, but we're assuming that the force is constant. All right, area under curve equals work. All right. So again, you could use calculus to do the fancy area under the curve, but we're not doing that, so we're just looking at a box. So since we're looking at a box, the force needs to be constant. All right, let's talk about one more concept. Okay, I'm going to erase this. What about time? Let's erase all this. All right, when we're asking how long does it take to get work done, right? Which is going to require more effort, all right? If I do my work quickly or I do my work slowly. Well, it's going to require more effort to do my work quickly, and we call that effort power. All right, power is the time rate of work. So it's basically the rate of work. Average power is equal to the work divided by the change in time. Okay, so the top we're just going to write our formula for work. All right. In the denominator, we'll just say it's a change in time. All right. The units, they'll be very familiar to you. They're going to be watts. All right. Watts is a capital W. Well, let's take a look at an example. Here's our box. We're going to apply a force of 15 newtons at an angle of 40 degrees. Okay, so again, we're going to want the component that's being applied parallel to the direction of the motion, and we're pushing it across a flat surface of 10 meters. And we're going to say that it takes 30 seconds. All right, we're going to say that it takes 30 seconds to move this object 10 meters when we're applying a force of 15 newtons at an angle of 40 degrees with the direction of our motion. So let's put the formula over here so I think it'd still be on the screen. Average power equals 15 newtons, that's our force, times the displacement of 10 meters, times the cosine of our angle, over the time in seconds. All right, and that average power is going to give us 3.8 watts. All right, now the question is, what if it takes 1 minute? All right, what if we're doing the work but it's taking us longer? How much power is being applied? Same formula, 15 newtons, same distance, same angle. All right, and I did this on purpose to just remember that we need our units in seconds if we want our final units to be in watts. All right, so we need, in order to get watts, we need joules over seconds. All right, so remember to change 1 minute to 60 seconds. And I did solve this and I got 1.9 watts. All right, so it takes half the amount of power if we're taking twice the amount of time in this case. All right, so this should give you a good head start on some of your questions as well as some of your practice. And when you do your reading will actually be on this, okay? I'm not going to require you to read something that is moving beyond, okay? You're just going to review in your reading and answer questions out of the book. All right.